Okay, last time we talked about spectral density. For energy signal, we have energy spectral density. For power signal, we have power spectral density. So today we are going to talk about a very special signal. A very special signal is noise. So when we talk about like mean value, variance, standard deviation, those things about noise, because knowing noise at this time or 10 minutes earlier does not mean anything we want to know, like noise power, right? Noise mean power, no, mean value, power, average value, all those things. So statistic parameters is important for random signals. Then we talk about a very important thing only for communication systems. Signal to noise ratio. This is one important parameter. We can tell how good or how bad is the system. Then we talk about correlation. Today we may not have time to talk about correlation. So when we talk about signal relationship, like one with itself and one with another. So we use autocorrelation, cross correlation to tell how close the two signals are with each other. So let's start with noise. So noise is a random signal. So even we know all the things about noise from current to many time ago. However, what happened in 10 seconds or even 1 second, we have no idea, right? It can be anything. So only those statistic parameters give us a hint what will be the noise line. So we talk about mean value, average. We use bar, right, to show mean value. So this is what we use in the textbook. So we just follow same notation. Okay, calculate mean value. Similar to you calculate power, right? We calculate the integral for your signal, normalized by t. But this time we don't have the square, right? We don't have the square, just the signal itself. So we get average over time. Later we show example how can we calculate a given signal's average value. Okay, second one, and this one is really important. Mean square value. It's also the power, right? Look at the equation, exactly the same as the one we calculate a signal's power. So square value and mean, right? We call it mean square value. So later if we say mean square value also mean the power, the same thing. So we calculate noise power by use 4.24. Okay. The third one is a new definition. We define AC component. Okay, here, something we already know, right? This is the average or mean. So your signal minus the average is kind of the signal oscillate, right? Around a baseline. The baseline we call it DC. And the value away from DC we call it AC component. And we use sigma. So we have definition for mean value, mean square value, and AC component. Any questions? Now we are going to use one example to show what's going on. Okay, this example from our textbook, 4.3.1. We have a signal given. Vt is 1 plus cosine omega 0t. We want to find three things about this one. Number one, average value, or also called mean value, right? B, AC power. We're going to explain this one very soon. 3, RMS value. So we have a new term, right? RMS value. So let's go through this example together. let me show you a little more details. Here, just same as your textbook. So example 1.341. Since my signal is periodical, right? So we can remove this limit. T goes to infinity. We just evaluate my signal in one period. Okay, for this one. If you are going to integrate a sinusoid signal, no matter it's cosine or sine, for whole period, one period, right, or two periods, or three periods, you will get zero. So look at this one. This is sinusoid, right? This is sine and cosine. So the red shaded area will be positive, right, when with the integral, and the purple one they are negative value. So if you add positive with negative, they are going to cancel with each other. Or zero. Sine, the same thing. So I'm going to get only DC components equation we get 1 here. So my mean value is 1. This one is straightforward. And now we want to know what is AC power. So over here, right? AC component is defined as NT minus NT average. Then we find this one's power. So So my sigma is 1 plus cosine omega 0 t, right? My mean value, I just calculate it, is 1. So my AC value is cosine omega 0 t, right? So my AC value is cosine omega 0 t. This is my AC value. AC power, my AC power. Just mentioned, AC power is also mean square value of your AC component. For this one, we try one more time. We have cosine omega 0 t squared, right? So this one is half 1 plus cosine 2 omega 0 t. We know the second part, integral from minus t over 2 to t over 2 will be 0, Again, right? So my final answer will be half. My AC power is half. Okay, integration of this one is 0. Is 0. Okay, so for question about part 2. Okay, part 3 is a little tricky because we just introduced a new concept, right, in this class. So let me open that. Over that. RMS. RMS value. So the definition of RMS value is mean square value, square root of your mean square value. So then we need to find mean square value first, right? Then square of it, we'll get our RMS value. So this is mean square value, right? Mean square value. And 1 plus 2 cosine of 2 plus cosine square dt. Okay, so we have square of the first term, square of the second term, and the cross term. So one thing I can tell, right? This one's 0. This one is no problem. Okay, I have sinusoid with integration for 1 period. Will give me 0 for sure. Okay, for this part, we just do the same procedure one more time. So let me write down for you. So 0, right?
Why did you put 1/2 in there twice? Why did you put 1/2 in there twice?
Yeah, because cosine square alpha is half 1 plus cosine 2 alpha. So half from here. Half is from here. Okay, so I have 1 plus half. All other terms, that's 0. My mean square value is 3 half. So one more step, right? Okay, so that's it, right? We get the RMS value. RMS value tells you the power of the signal. Peak-to-peak value will tell you the dynamic range of the power. So if you have a very smart scope, right, you look at RMS value, it tells you the power. Okay. So almost the same, right? Just I add a little more details here. How can you this one? So I'm going to